Eternity blockchain. The trustless, decentralized and purely functional Oracle machine. January 23, 2017 v0.1 Zackary Hess Zack, at Eternity.com Yanislav Malahov Yani, at Eternity.com Jack Pettersson Jack, at Eternity.com Abstract. Since the introduction of Ethereum in 2014, there has been great interest in decentralized trustless applications, smart contracts. Consequently, many have tried to implement applications with real-world data on top of a blockchain. We believe that storing the application's state and code on-chain is wrong for several reasons. We present a highly scalable blockchain architecture with a consensus mechanism which is also used to check the oracle. This makes the oracle very efficient, because it avoids layering one consensus mechanism on top of another. State channels are integrated to increase privacy and scalability. Tokens and channels can be transferred using purely functional smart contracts that can access oracle answers. By not storing contract code or state on-chain, we are able to make smart contracts easier to analyze and faster to process, with no substantial loss in de facto functionality. Applications like markets for synthetic assets and prediction markets can be efficiently implemented at global scale. Several parts have proof-of-concept implementations in Erlang. Development tools and application essentials such as a wallet, naming and identity system will also be provided. Introduction. The intention of this paper is to give an overview of the Eternity blockchain architecture and possible applications. More detailed papers will be released in the future, specifically for the consensus and governance mechanisms. However, it should be noted that our architecture is holistic. All components tie together and synergize, in a modular way. The rest of this paper is broken into 4 parts. First, we will introduce and discuss the fundamental theoretical ideas that inform our architecture. Second, we will discuss the included essential applications, other possible use cases and give intuitions for how to use the platform as a developer. Third, we will present the current proof-of-concept implementation, written in Erlang. We conclude with a discussion, including possible future directions and comparisons to other technologies. Previous work. Blockchains, first of all Bitcoin, have shown a new way to architect value exchange on the Internet. 1. This has been followed by a number of promising advances. Ethereum demonstrated a way to write to complete smart contracts secured by a blockchain architecture. 2. Trustcoin created tools for making oracles on blockchains. 3. While Group Gnosis and Augur showed how to make them more efficient. 4. Casey Detrio showed how to make markets on blockchains. 5. Namacoin showed how to make the distributed equivalent of a domain name server. 6. Factum showed how a blockchain that stores hashes can be used as a proof of existence for any digital data. 7. These technologies show great promise when it comes to providing first-class financial and legal services to anyone. So far, however, they have failed to come together to a unified whole that actually fulfills the promise. Specifically, all solutions so far have been lacking in at least one of the following respects: governance, scalability, scripting safety and cheap access to real-world data. Needs it. Eternity aims to improve the state-of-the-art in all of these respects too. Eternity blockchain. We believe that the lack of scalability, scripting safety and cheap access to real-world data of current smart contract platforms come down to 3 core issues. First, the currently prevailing stateful design makes smart contracts written for the platform hard to analyze. 1. And statefulness combined with sequential transaction ordering complicates scalability. Needs it. Second, the high cost of bringing real-world data into the system in a decentralized, trustless and reliable way complicates or outright prevents the realization of many promising applications. Needs it. Third, the platforms are limited in their abilities to update themselves, in order to adapt to new technological or economical knowledge. We believe that each of these 3 problems have clear solution paths that should be explored. First, recent research into state channel technology suggests that for many use cases, keeping state on-chain is not necessary. Needs it. It is very often entirely possible to store all information in state channels, and only use the blockchain to settle any economic results of the information exchange, and as a fallback in the case of dispute. This suggests an alternative approach to blockchain architecture in which Turing-complete smart contracts exist in state channels but not on-chain. This increases scalability since all transactions. 1. The difficulty of analyzing stateful contracts was very clearly demonstrated by the re-entrance bug that brought down the DAO. This happened despite the code having been audited by several of Ethereum's creators as well as the general community. Needs it become independent and can thus be processed in parallel. Additionally, this means that contracts never W also has to pay a small fee for the amount of time it is open. The costs of creating and keeping accounts prevent spam and disincentivizes state bloat. The reward for deleting accounts incentivizes the reclaiming of space. 3. Name system. Many blockchain systems suffer from unreadable addresses for their users. In the vein of Aaron Swartz's work and Namacoin, Aeternity features a name system that is both decentralized and secure, while still supporting human-friendly names. 9. The blockchain state includes a mapping from unique human-friendly strings to fixed-size byte arrays. These names can be used to point to things such as account addresses on Eternity, or hashes for example of Merkle trees. 4. Block contents. Each block contains the following components, the hash of the previous block, a Merkle tree of transactions, a Merkle tree of accounts, a Merkle tree of names, a Merkle tree of open channels, a Merkle tree of oracles which haven't answered their respective questions, a Merkle tree of oracle answers, a Merkle tree of Merkle proofs, the current entropy in the random number generator. The hash of the previous block is required to maintain an ordering of the blockchain. The transaction tree contains all transactions that are included in the current block, with the exception of the consensus vote tree. All the trees are fully under consensus. If a tree is changed from one block to the next, this change has to be due to a transaction in the new block's transaction tree, and a Merkle proof of the update has to be included in the block's proof tree. The purpose of the 3 remaining trees will hopefully become clear in the following sections. State channels. One of the most interesting developments in the blockchain space lately is that of state channels. They operate on the basic principle that in most cases, only the people affected by a transaction need to know about it. In essence, the transacting parties instantiate some state on a blockchain, for example an Ethereum contract or a Bitcoin multisig. They then simply send signed updates to this state between each other. The key point is that either one of them could use these to update the state on the blockchain, but in most cases, they don't. This allows for transactions to be conducted as fast as information can be transmitted and processed by the parties, instead of them having to wait until the transaction has been validated and potentially finalized by the blockchain's consensus mechanism. On Eternity, the only state update that can be settled on the blockchain is a transfer of ion, and the only ion that can be transferred are the ones that the transacting parties already deposited into the channel. This makes all channels independent from each other, which has the immediate BNY1 macro gold F878 F615 B386 AAD5 B953 F089 23 gold Oracle 4 F01000 L00 and 50 Figure 1, a simple contract encoding a bet on the price of gold. The language used is the Forth-like Chalang, which will be presented in section IV. Fit that any transactions related to channels can be processed in parallel, greatly improving transaction throughput. The blockchain is only used to settle the final outcome or to resolve conflicts that arise, roughly analogous to the judicial system. However, because the blockchain's behavior will be predictable, there is no gain in disputing the intended result of a state channel. Malicious actors are incentivized to behave correctly and only settle the final state on the blockchain. All taken together, this increases transaction speed and volume by several orders of magnitude, as well as privacy. 1. Smart contracts. Despite that the only state that can be settled on-chain is a transfer of ion, Aeternity still features a Turing-complete virtual machine that can run smart contracts. Contracts on Eternity are strictly agreements that distribute funds according to some rules, which stands in stark contrast to the entity-like contracts of, for example, Ethereum. Two of the more notable practical differences is that by default, only the involved parties know about a given contract, and only parties that have an open state channel can create a valid contract. If the parties agree to a contract, they sign it and keep copies for future reference. It is only submitted to the blockchain if its outcome is disputed, in which case the code is only ever stored as part of the submitted transaction, never in any other state. If this happens, the blockchain distributes the tokens according to the contract and closes the channel. As an example, Figure 1 shows a very simple contract that encodes a bet on the price of gold at a certain time. On line 1, the macro gold saves the identifier of the oracle in question, which will return true if the price of gold is below $38 G on December 1, 2016. The body of the contract is displayed on lines 2-4. We first push the gold oracle's identifier to the stack and call it using oracle, which will leave the oracle's answer on the top of the stack. We use this to do a conditional branching. If the oracle returns true, we push 0 and 1000 to the stack, indicating that 0 EN should be burned and 1000 EN should go to the first participant in the channel. Otherwise, we push 0 and 0, with the second 0 indicating that the other participant receives all in the channel. Finally, we push 0, which is taken to be the nonce of this channel state. In actual usage, the nonce would be generated at deployment. One important thing to note is that contracts on Aeternity don't maintain any state of their own. Any state is maintained by the transacting parties and submitted as input at execution. Every contract is essentially a pure function that takes some 3-1. #lock2 swap 3 #4 == Figure 2. A simple #lock1 macro commitment a 9D78023 F80AC 8,928,334. 2-3 commitment #lock call for if 0-100 else 0-50 and 5-1 figure 3. Using the #lock to trustlessly send tokens through a middleman input and gives a new channel state as output 2. The benefits of using pure functions in software development in general, and in the development of financial applications in particular, has been extensively documented in academia and industry for decades. 10. Need setup, contract interaction and multi-step contracts. Even though all contracts are stateless and execute independently of each other, contract interaction and statefulness can still be achieved through #looking. Needset. A simple #lock is shown in figure 2. On line 1, we define a function called #lock that expects the stack to contain a #h and a secret s. It swaps them on line 2, in order to hash the secret on line 3, before calling the equality operator on #v and h on line 4. This returns true with the secret as a preimage of the hash. This function can be used to predicate the execution of code branches in different contracts on the existence of the same secret value. As a simple example usage, #locks make it possible for users that don't share a state channel to trustlessly send each other in, as long as there is a path of channels between them. For example, if Alice and Bob have a channel and Bob and Carol have a channel, then Alice and Carol can transact through Bob. They do this by creating 2 copies of the contract shown in figure 3, one for each channel. The commitment on line 1 is the hash of a secret that Alice chooses. On line 3 we push it to the stack and call the #lock function. Which branch of the if that gets executed depends on the return value of #lock. Once these contracts have been signed by all parties, Alice reveals the secret, allowing Bob and Carol to use it to claim their EN. #locking can also be used to, for example, play multiplayer games in the channels. As shown in figure 4, everyone makes a channel with a game manager, which publishes the same contract to every channel. Say we are in game state 32. It should be noted that since contracts can read answers from oracles and some environment parameters, they aren't completely pure functions. However, oracle answers never change once they've been provided and can be argued to be due to the computational richness of the oracle machine, rather than being an impurity. Environment parameters are deemed a necessary evil and will ideally be compartmentalized appropriately by high-level languages. 1 macro commitment a 9D78023 F80AC 8,928,334. 2-3 commitment #lock call for if state 33 else state 32 and 5 call figure 4. A simplified example of using the #lock to play a multiplayer game in channels defined by the function state 32. And we want to trustlessly simultaneously update all the channels to state 33. When the game manager reveals the secret, it causes all the channels to update at the same time. B. Metered execution. Contract execution is metered in a way similar to Ethereum's gas, but Aeternity uses 2 different resources for its metering, one for time and one for space. Both of these are paid for using EN by the party that requests the execution. This could be seen as undesirable, because it is probably another party that is causing the need for the blockchain to resolve the dispute in the first place. However, as long as all money in the channel is not used for betting, this can be effectively nullified in the contract code, since it has the ability to redistribute funds from one party to the other. It is in fact generally good practice to avoid using all funds in a channel to transact, because it disincentivizes the losing party to cooperate when closing the channel. B. 2. Example. Let's bring all of these ideas down to earth. In practice, if Alice and Bob want to transact using a state channel on Aeternity, they go through the following procedure. 1. Alice and Bob sign a transaction that specifies how much money each of them is depositing into the channel, and publish it to the blockchain. 2. Once the blockchain has opened the channel, they can both create new channel states, send them between each other and sign them. Channel states can be either a new distribution of the funds in the channel or a contract that determines a new distribution. Each of these channel states has an increasing nonce and are signed by both parties, so if a dispute arises, the latest valid state can be submitted to the blockchain, which enforces it. 3. The channel can be closed in two different ways. If Alice and Bob decide that they have finished transacting and agree on their final balances, they both sign a transaction indicating this and submit it to the blockchain, which will close the channel and redistribute the money in the channel accordingly. B. If Alice refuses to sign a closing transaction for any reason, Bob can submit the last state that both of them sign and request to have the channel closed using this state. This starts a countdown. If Alice believes that Bob is being dishonest, she has the opportunity to publish a state with 4 higher nonce that both of them have signed before the countdown finishes. If she does so, the channel closes immediately. Otherwise it closes when the countdown has finished. See consensus mechanism. Aeternity uses a hybrid proof-of-work and proof-of-stake consensus mechanism. The block order will be determined via proof-of-work. Certain system variables will be determined via on-chain prediction market system, which allows the users to participate and bring in their knowledge. For the POW algorithm, we currently favor a variant of Trump's cuckoo cycle, one which is memory-bound, and also is an indirectly useful proof-of-work, as it requires less electricity to run, but instead has another limiting factor, the one of memory latency availability. This also makes it feasible to mine with the smartphone. Trump writes about his work. Cuckoo cycle is an instantly verifiable memory-bound POW that is unique in being dominated by latency rather than computation. In that sense, mining cuckoo cycle is a form of ASIC mining where DRAM chips serve the application of randomly reading and writing billions of bits, when even phones charging overnight can mine without orders of magnitude loss in efficiency. Not with the mindset of profitability but of playing the lottery, the mining hardware landscape will see vast expansion, benefiting adoption as well as decentralization. Preview. The consensus mechanism has a somewhat non-standard role in Aeternity. In addition to agreeing on new blocks for the blockchain, it also agrees on both answers to Oracle questions and the values of the system's parameters. In particular, the consensus mechanism can change itself. However, it should be noted that this is not entirely unproblematic. For example, if a simple proof-of-work mechanism was used, it would be rather cheap to bribe the miners to corrupt the Oracle. Therefore, Aeternity is going to use a novel hybrid proof-of-stake proof-of-work algorithm, leveraging the benefits of both. Independently from this, POW is going to be used to issue new IAN tokens. Side note, originally Aeternity intended to be a 100% proof-of-stake blockchain. We don't think anymore that a decentralized 100% POS system is possible. C. 1. Oracles. A crucial feature for most contracts, whether encoded as text or as code, is the ability to refer to values from the environment, such as the prices of different goods or whether a certain event occurred or not. A smart contract system without this ability is essentially a closed system and arguably not very useful. This is a generally accepted fact, and there are already several projects that attempt to bring external data into the blockchain in decentralized way. 8. However, to decide whether a supplied fact is true or not, these essentially require the implementation of a new consensus mechanism on top of the consensus mechanism. Running two consensus mechanisms on top of each other is as expensive as running both separately. Additionally, it doesn't increase security, because the least secure one can still be attacked and made to produce false values. Thus, we propose to conflate the two consensus mechanisms into one, essentially reusing the mechanism that we used to agree on the state of the system, to also agree on the state of the outside world. The way that this works is as follows. Any IAN holder can launch an oracle by committing to answering a yes/no question. When doing so, they also need to specify the time frame during which the question can be answered, which can start now or sometime in the future. The user that launches the oracle is required to deposit IAN in proportion to the length of the time frame, which will be returned if the user supplies an answer that gets accepted as truth. Otherwise it is burned. The blockchain generates a unique identifier for the oracle that can be used to retrieve the answer once it is available. Once the time comes for the question to be answered, the user who launched the oracle can supply an answer for free. Once the oracle launcher has supplied an answer or until a certain amount of time has passed, any other users can submit counterclaims by depositing the same amount of IAN. If no counterclaims have been submitted by the end of the time frame, the answer supplied by the user that launched the oracle is accepted as truth, and the deposit is returned. If any counterclaims are submitted, then the consensus mechanism for blocks will be used to answer the oracle. This is more expensive, but since we know we can take at least one of the two safety deposits, we can use it. Governance of blockchain-based systems has been a big problem in the past. Whenever a system upgrade needs to be done, this requires a hard fork, which usually leads to big discussions among all value holders. Even simple things, like correcting an arbitrarily set variable in the source code, as we have seen with the block size debate in Bitcoin, seem to be very hard in a system where the user's incentives are not aligned with the decision makers, and where there is no clear upgrade path. We have also seen more complicated governance decisions, like fixing a single smart contract bug in the DAO, which required quick intervention by system developers. The primary problem of these systems is easily identifiable. The decision-making process for a protocol upgrade or change is not well defined and lacks transparency. Aeternity's governance system is part of the consensus. It uses prediction markets to function as efficiently and transparently as possible. Moreover, the consensus mechanism is defined by a number of variables that determine how the system functions and that are being slightly updated by each new block, from how much it costs to make transactions or ask an oracle, to modifications of fundamental parameter values like the block time 5. By having prediction markets about the variables that define the protocol, the users can learn how to efficiently improve the protocol. By having predictions markets about potential hard forks, we can help the community come to consensus about which version of the code to use. Each user chooses for itself which metric it seeks to optimize, but a simple default strategy would be to maximize the value of its holdings. Scalability 1. Sharding trees. The architecture that has been presented thus far is highly scalable. It is possible to run the blockchain even when each user only keeps track of the part of the blockchain state that they care about and ignores everyone else's data. At least one copy of the state is needed for new users to be certain about the substate that they care about. But we can shard this data across arbitrarily many nodes so that each node's load is arbitrarily small. Merkle trees are used to prove that a substate is part of the state. 11. It is easy to imagine a scenario where certain nodes specialize on keeping track of the trees and get paid for inserts and lookups. 2. Light clients. Light clients don't download the entire blocks. First, the user gives their client a hash in the history of the fork they prefer, a technique also known as weak subjectivity. 12. Then the client knows only to download forks that include a block with that hash. The client only downloads the headers of the blocks. The headers are much smaller than full blocks. Very few transactions are processed. For simplicity, we made no mention of the block headers when discussing the block structure in section 2a. 4. But they contain the following: the hash of the previous block, the root hash of all of the state trees. 3. State channels and parallelism. State channels have immense throughput and most transactions inside them are never executed or even recorded on the blockchain. Additionally, the channels don't write to any shared state on chain, so all transactions that actually do get recorded on the blockchain can be processed in parallel. Given that most consumer hardware sold today has at least 4 processing cores, this has the immediate effect that transaction throughput is multiplied by roughly a factor of 4. Furthermore, the fact that there will never be any complex concurrent interaction suggests that sharding this blockchain architecture should be relatively easy. Since blockchain sharding is still fairly experimental, we have deliberately chosen not to pursue any sharding techniques in the initial design of Aeternity. However, if this changes in the future, Aeternity should be one of the easiest blockchains to shard. 4. Transactions per second at a given memory requirement. The variables that define the protocol are all constantly being updated by the consensus. From their initial default values, we can calculate the initial default rate of transactions per second. Note that this is a draft and will likely to change 4 we define the following variables for the following calculations. 6b equals block size in bytes, 7f equals blocks till a finality, hr equals time till a finality in seconds, 9t equals transaction size in bytes, 1011 transactions per second equals bf, tr. 1213b equals 1 million bytes equals 1 megabyte per block, 14f equals 2462 blocks per day, 15rf equals 30 seconds per block, 16r equals 3600 seconds per day, 17t equals 1000 bytes per transaction, 1819 10000000, 2462 1000 24 3620 equals 1,000,1030 21 equals ca. 32 transactions per second. Fast enough to sign up every human within 8 years. To operate a node, We need to keep a copy of all the blocks since finality, and we need to be able to record 100 times more information, in case there is an attack. Estimating that finality is 2 days, then there would be 5,760 blocks till finality, so the memory requirement is 5,761 megabyte 100 equals 576,000 megabytes equals 576 gigabytes. When there isn't an attack happening, one would only need about 5.76 gigabytes to store the blocks. 3. Applications. The stateless nature of the Eternity smart contracts makes it easy to build the following applications on Eternity's blockchain. It is especially suitable for high-volume use cases. A. Blockchain essentials. Blockchain essentials are necessary primitives like yani, wallets, names and related concepts. They modularize reusable components which can be used as application foundations and can be improved on. A. 1. Identities. Each account will have an associated unique ID number. Users can register unique names and link names to the Merkle root of a data structure. The data structure can contain one's unique ID as well as other information about one's account. We aim to use schema.org's JSON format to represent things like persons or companies. 13. A. 2. Wallet. A wallet is a piece of software that is used to interact with Eternity. A wallet manages private keys for the yani and creates and signs transactions. One can use the wallet to send channel transactions and use apps in the channel network. A. 3. Proof of existence. One transaction type allows for the publishing of the hash of any data. System participants can use the headers to prove that the data existed at that point in time. 6b. State channel applications. Smart contracts in state channels are perfect for microservices on the web that require a high transaction throughput. B. 1. Toll API. Most APIs existing today are publicly available for anyone to call, or else they are secured by a username password scheme or unique access tokens. Payment channels allow for a new kind of API, where one pays for every call to the API, possibly every HTTP request. Paying to access an API solves DDoS problems, and it makes it easier to build high-quality APIs that are always available. API responses that require a payment are fundamental for the creation of as of yet impossible types of businesses and can play an important role in the emergence of the decentralized economy. They create incentives for information owners to make otherwise private data publicly available. B. 2. Insured crowdfunding. We can implement insured crowdfunding using dominant assurance contracts. NEEDSIT. These are smart contracts that are used to raise money for a public good, like a new bridge, a school or a market. Dominant assurance contracts differ from traditional assurance contracts like Kickstarter, in that they make it a dominant strategy to participate. If the good is not funded, all participants get their in back plus interest, so they are insured against reducing their liquidity without receiving the good. Using an oracle, we can ensure that the provider of the good or service only gets paid if the good or service is actually provided. B. 3. Cross-chain atomic swaps. Cross-chain atomic swaps allow for trustless exchange of yani for bitcoins. 14. 15. These can be implemented using a hash lock that locks the transactions on both blockchains under the same value. B. 4. Stable value assets and portfolio replication. We can use smart contracts to program synthetic assets that stay nearly the same price as a real-world asset. For example, we could make an asset that stays the same price as gold. Synthetic derivatives are created in equal and opposite pairs. For one user to have an asset that moves with gold, a different user will have to have an asset that moves inversely to gold. For example, Alice could make a contract with Bob so that Alice owns 1 gram of gold. Out of the money in the contract, 1 gram of gold worth of yani will go to Alice, and the leftover money goes to Bob. The contract has an expiration date when the price of gold will be measured, and the funds distributed to Alice and Bob accordingly. B. 5. Event contracts. Event contracts pay when an event happens and don't pay when an event does not happen, as per the oracle's telling. Apart from being interesting in themselves, these can be used by several different applications. Insurances. We can use event contracts to implement insurances. For example, expensive music event tickets can become worthless if the weather goes bad. However, if the concert goer receives money if the oracle decides that it rained on the day of the event, the investment can be protected so that one can afford to find an emotionally adequate alternative. Slightly more seriously, farmers are often interested in the total number of inches of rain in a season. We can insure them against their crops wilting from dryness. B. Whistleblowing. Event contracts can also be used to incentivize revealing sensitive information. For example, we could bet on the event information indicating that company A has used illegal pesticides was released on or before January 24, 2017 inches. Any person with access to such information would be incentivized to first bet that the event will happen and then release it. B. 6. Prediction markets. A prediction market works by letting users bet on whether a future event will happen. From the price of the bets we can predict the future likelihood. 3. 8. 16. They are the most accurate way to measure the future at a given price. Need set. Once the event has happened, the market is settled using the oracle. As noted in section 2D, we can for example use prediction markets to predict which updates to the software will be beneficial, and which will be harmful. We can also use them to estimate how much candidates in an election will actually be able to accomplish, so lies and baseless promises can be detected more easily. Figure 5. Multidimensional prediction market. Multidimensional prediction markets. Multidimensional prediction markets allow us to predict the correlation between possible future events. So for example, one could predict that if Alice is elected leader, the price of potatoes will go down, and that if Bob wins, the price will go up. One could learn that if Google uses Plan A for the next 3 months, that it will probably earn more money, and that if it uses Plan B, it will probably earn less. Or, as in Figure 5, we can see that if Alice would be elected president, there is a high likelihood of the price of potatoes being rather low. B. 7. Market with batch trading at a single price. There are two approaches available to attackers that want to rob in from a market. They can take advantage of the market being split in time, or they can take advantage of it being split in space. If the market is split in space, then the attacker does arbitrage. He simultaneously makes trades in both markets at once so that his risk cancels out and he earns a 7 profit. If the market is split in time, then the attacker front runs the market. He reads the transactions coming into the market and creates buy and sell orders immediately before and after. Figure 6. The black line is the demand curve. The red line is the supply curve. The sells in red are the same size as the buys in red. The vertical line is the price the market maker selected. Everyone willing to buy at a higher price traded at that price. Everyone willing to sell at a lower price traded at that price. To combine markets in space, everyone should use the same market maker. To combine markets in time, we need to have trading done in batches, at single price. The market maker needs to commit to each person what price he decided, and if anyone can find contradictory commitments from the market maker, then all of his customers should be able to drain all of his channels. If the market maker commits to a fair price, then he will match the same volume of buyers and sellers together, as Figure 6 shows. Otherwise, he will end up in a situation similar to Figure 7, thus taking a large risk. Figure 7. The black is much bigger than the red. The market maker is selling many more shares than it is buying, thus taking on a lot of risk. 4. Implementation. Most key concepts already have proof of concept implementations in Erlang. This includes the blockchain itself, the contract language and VM, the oracle and governance mechanisms, as well as an old version of the consensus mechanism. We have used Erlang OTP because it makes it easy to write code that can respond to many requests in parallel and does not crash. The servers with the highest uptime in the world are based on Erlang. It has been used for industrial applications for 30 years, proving itself to be a reliable and stable product. A virtual machine in contract language. The virtual machine is stack-based and similar to Forth and Bitcoin scripting language, although in comparison to the latter, it is rather rich. The VM supports functions instead of gotos, making its semantics relatively simple to analyze. A list of the VM's opcodes can be found on our GitHub 3. Additionally, there exists a higher-level Forth-like language called Erlang, which compiles to bytecode for the VM. It supports macros and variable names, but keeps the stack-based execution model. 17. Examples of Erlang code can also be found on our GitHub 4. B. Adoption via web integration. The web is the most popular application platform. We will provide easy-to-use web development tools, such as JS libraries and JSON APIs for the core features of the Aeternity blockchain. See open-source modules in order to be easily reused for private blockchain consortium and other use cases. The software will be written in MIT-licensed modules, such as a consensus module, that can be adapted to specific needs. Usability and UX design. Frictionless human interaction will be a big focus of our development efforts. More specifically, we will make sure that who controls the identity, keys and transactions is clearly established. Also, offering easy access via web gateways will be a central focus of future development. Users participating in prediction markets via a Tinder-like, swipe left-right, mobile interface, and simple web wallets that can be easily integrated in a website through an iframe will be the new norm. The discussion we have provided an explanation of how to architect a fundamentally more efficient value transfer system. The described system is in fact a global Oracle machine that can be used to provide decision-making services at global scale. In particular, all the applications proposed in Section 3 can be built easily and efficiently on top of Aeternity 3 https://github.com/eternity/challenge/blub/master opcodes md4 https://github.com/eternity/challenge/tree/master examples 8. However, our approach has both fundamental limitations and avenues for improvement. These are discussed here. Limitations and trade-offs. While we do believe that the trade-offs made in our architecture are reasonable given the resulting performance increase in other areas, Aeternity is not a catch-all solution for decentralized applications. It should rather be viewed as a synergistic complement to existing technologies. There are several caveats that one need to be aware of. 1. On-chain state. Despite having many advantages, Aeternity's lack of programmable state makes it unfit for applications that require a custom state to be under consensus. For example, this includes DAOs as they are usually conceived, custom name systems and subcurrencies which are not tied to the value of an underlying asset. 2. Free option problem. If Alice and Bob have a channel and Alice signs a contract, she essentially gives Bob a free option when she sends it to him. Bob can choose to sign and return, that is activate, the contract at any time in the future. Often this is not what is intended. To avoid this problem, channel contracts aren't immediately activated with the full amount. They are divided up in time or space. Both participants would sign up for the contract in small intervals so that neither user ever offers a large free option to the other. For example, if the parties want to bet 100 yen, then they might sign up to it in 1,000 steps that each increase the bet by 0.1 yen. This would require about 1,000 messages to pass, 500 in each direction, which is cheap enough since the contract is never submitted to the blockchain. As another example, if one wanted to make a financial asset that would last for 100 days, one might sign up in 2,400 steps of 1 hour each. This would require about 2,400 messages to pass, 1,200 in each direction. 3. Liquidity loss in state channel topologies. When composing channels using hash locks as demonstrated in Section 2b, 1. Any middlemen have to lock up at least twice as many yen as will be transmitted through them. For example, if Alice and Carol want to transact through Bob, Bob will act as Carol when interacting with Alice, and vice versa. Since this is expensive for Bob, he would most likely earn a fee as compensation. If Alice and Carol expect to conduct many trades between each other, they can avoid this by creating a new channel and trustlessly moving the active contracts to the new channel using a hash lock. Still, since keeping an extra channel open impacts one's liquidity negatively, going through middlemen is expected to be desirable in many cases, especially in cases where the parties don't expect to trade a lot in the future. Thus, a channel topology where certain rich users make money from trustlessly transmitting transactions between other users is expected to emerge. It should be noted that this does not constitute a single point of failure, since we do not trust these transaction transmitters with anything. If a transmitter goes offline before the secret to a hash lock has been revealed, the transaction doesn't go through. If it goes offline afterwards, the only possible negative effect is that the transmitter is not able to claim its yen. Future work. There are several possible ways to improve on the current architecture. 1. Functional contract language. A reasonable future direction would be to experiment with high-level languages that adhere more closely to the functional paradigm. Keeping track of an implicit stack is generally error-prone and arguably not suitable for a high-level, developer-facing language. This should be rather easy given that programs are already pure functions, modulo some environment variables, and would greatly simplify both development and formal verification of contracts. If this is done, it could also make sense to revise the VM to be tightly coupled with the new language, to make the compilation less error-prone and less dependent on trust in the developers. Ideally, the translation from surface language to VM code would simply be a direct transcription of peer-reviewed research, though pragmatic concessions will likely have to be made. 2. Multi-party channels. Currently, all channels on Aeternity are limited to 2 parties. While multi-party channels can de facto be achieved through hash looking, this can be expensive. Hence, we plan to investigate the possibility of adding support for n-party channels, with a MOVN settlement mechanism. Glossary blockchain. A distributed, tamper-proof database with metered access. The database is defined by a growing list of hash-linked blocks and can have any rules for appending them. Yani represents an unit of account and an access right to the Aeternity blockchain. It is transferable. Transaction. A message from a user to the blockchain. This is how users can use their currency to access the blockchain. State channel. A relationship between two users recorded on the blockchain. It enables users to send ION back and forth, and to create trustless smart contracts between them that are enforced and settled by the blockchain. Hash. A hash takes as input a binary of any size. It gives a fixed-sized output. The same input always hashes to the same output. Given an output, one cannot calculate the input. Hash looking. This is how we connect pairs of channels to make smart contracts that involve more than two people. A secret is referenced by its hash. When the secret is revealed, it can update multiple channels at the same time. Governance. A well-defined process of making decisions for the future protocol of the blockchain. 9. Oracle. A mechanism that tells the blockchain facts about the world we live in. Using oracles, users can predict the outcome of events external to the blockchain system. Value holder and user who owns ION, or an financial derivative in the system. Validator. A validator is an user who participates in the consensus mechanism. In the case of Eternity, every value holder can participate. Acknowledgements. Thanks to Vlad, Matt, Paul, Dirk, Martin, Alistair, Devin and Ben for proofreading. Thanks to these and lots of other people for insightful discussions. References. 1. S. Nakamoto, Bitcoin, a peer-to-peer electronic cash system. 2008. Online. Available. https bitcoin.org Bitcoin PDF. 2. V. Buterin, Ethereum, a next-generation smart contract and decentralized application platform. 2014. Online. Available. https github.com Ethereum Wiki White Paper. 3. Piece to Work. Market Empiricism. Online. Available. http://bitcoinhivamind.com/papers/one-purpose PDF. 4. M. Liston and M. Koppelman, A Visit to the Oracle, 2016. Online. Available. https://blognosis.pm. 5. C. Dutrio, Smart Markets for Smart Contracts, 2015. Online. Available. http://c.r.io/smartmarkets/6. Namacoin Wiki, 2016. Online. Available. https://wikinamacoin.org Index PHP Title = Welcome. 7. P. Snow, B. Deary, J. Liu, et al. Factum. Business processes secured by immutable audit trails on the blockchain. 2014. Online. Available. http://provencoin.com Assets White Papers Factum White Paper PDF. 8. J. Pettersson and J. Krug, Augur, a decentralized, open-source platform for prediction markets. 2014. Online. Available. http://provencoin.com Assets White Papers Augur, a decentralized open-source platform for prediction markets PDF. 9. A. Schwartz, Squaring the Triangle, Secure, Decentralized, Human-Readable Names. 2011. Online. Available. http://www.aronswicom Weblog Square Azuko. 10. T. Hvitvt, A Survey of Formal Languages for Contracts, Informal Languages and Analysis of Contract-Oriented Software. 2010. Pages 29-32. Online. Available. http://www.dikudkhjmezitaransat Hvit Publications Hvit 10 Flakos PDF.